Part of which he's going to present here. So I am very happy to introduce you to Mars. So, and he's also given a talk before on this subject, which you can find on our YouTube channel. So, other than that, his interests are also comets and asteroids and dust particles between the planets. So, he tries to find options. Thank you very much. Welcome, Jeremie.
Thank you very much, Samir. Thank you very much for the introduction, and thank you very much, everyone, for the welcome. It's always a real pleasure for me to come back in India, like Samir was saying. I've been working with colleagues in IUCAA for almost 20 years now, especially Professor Gupta. And so tonight, I'd like to present to you some work that we have been doing on trying to decipher the mystery of comets, and especially it might not be so well known amongst yourselves that the European Space Agency have done a lot of work regarding studying those objects using spacecraft. So I know NASA does a lot of work with respect to comets and small bodies, and has sent a number of missions already, but I'm not going to talk about those for this presentation tonight. And also I would like, before we start on those space missions, I would like to congratulate India once again, because that's been 1 year that you successfully landed on the south polar side of the moon with Chandrayaan 3. And so congratulations to you, it's always great. But that's not my field. I'm more specialized into working with the space missions from Europe. I'm located in France. And so this is the kind of topics I'm going to present to you tonight. First, I'd like to give you a little bit of history and a little bit of background about what comets objects are. And then I'm going to describe to you, relatively briefly, the three different programs that we have for exploring comets. Giotto was in 1980s, Rosetta happened in the last 10 years, and Comet Interceptor is the next one, the one that we are preparing for the coming years that you will probably hear about later. So a little bit of history about comets. Those objects are extremely spectacular. They are usually, you know, the ones that you like to show on the, you know, the sky maps of young kids or children for going to sleep. Those are the, you know, like those kind of heavy stars. They are not predictable. They are not periodic. They look like nothing else that you can see typically on the night sky, like the stars or the planets. So that's why the ancients in ancient cultures, they were thought to be actually bad omens, or messages from the gods, essentially. And actually, Seneca, actually in writing his treatise about comets, already noticed in that book that the trajectories are not limited to the ecliptic. The ecliptic is the plane where the planets are moving around the sun. And the comets are actually objects that go beyond that plane or at given angles with respect to that plane. So they are completely different from the solar system objects that the ancients could see in the sky. Usually they were feared, and they were related to wars, pandemics. This is actually the Neowise Comet. It was a very, very bright comet in 2020, and if the ancients were still here, ancient Greeks, ancient Romans, they would have thought this was the pandemic comet, associated with this kind of problems on the Earth. But they were trying to get messages from the sky. There's only one historically good comet, and it is represented here. There was a comet that appeared after the death of Julius Caesar, and it was interpreted as his soul going up to the sky to belong into the godly regions. Similarly, because the regions of the sky were supposed to be perfect where the gods reside, Aristotle actually thought that the comets were not objects that belong to the solar system or to the star region, but belong to the terrestrial region. And for practically 2,000 years, that was the predominant theory about comets, that comets are not belonging in the star or the planet region. Comets actually are meteorological phenomena that were created into the atmosphere. So that was the dominant theory for a very, very long time. But here, during the Renaissance, so a few scientists actually started to study comets as proper objects. And they started to realize that those really it doesn't make sense for them to belong to the terrestrial rim. Appian actually published a number of observations where he noticed that the tail of the comet is always directed opposite to the position of the sun. This is an observation that was actually done earlier by the Chinese. But in this description, we can clearly see that there should be a link between comet and sun. But we also know that possibly the sun could affect the Earth's atmosphere. So that is not a good evidence for showing that the comets are among the stars. The best one was done by Tycho Brahe, the famous astronomer, that Kepler used this data in order to get the laws of the motion of the planets around the sun. He observed a comet using the parallax. So at two different angles, he could see the object with respect to the fixed stars beyond. And given that angle, he could see that it was further away from the Earth, further away than the moon from the Earth. So you've got the Earth here, the moon here, and the comet is much beyond. So clearly, based on these observations, the comet was part of the solar system. And then he created his own model of the solar system, which was a mix between the Copernican and the Aristotelian solar system. You've got the Earth here, the moon rotating around the Earth, the sun rotating around the moon-Earth system, and all the other planets are rotating around the sun. Well, the comets are very, very difficult objects to predict. Kepler could devise this law by using the observations of Tycho Brahe. Whatever new theory you would have to, you would come with in order to explain the motion of planets, because now the comets belong with the planets, you would need to have a theory that would also explain the motion of comets. And that's exactly what happened with Newton. So you know all about Newton because he's located in the garden nearby at IUCAA, right? That's where I took the picture. But he devised his general theory for gravitation, explaining that the forces that are applied from the Earth to the moon are exactly the same as the forces that are applied from the Earth to apples or to us. That's why we are not, flying into the air. That's because the Earth is attracting us. And that's the same thing that happens between the sun and all the planets around the solar system. If this is correct, then comets, those most irregular objects, should also, be explained by these kind of laws. And he spent a big part of his, Principia Mathematica, applying his new laws to a comet that he actually himself observed in 1680. And this is one of the few drawings that you find in that book where he indeed actually applies his law, because the 1/r squared distance law for the gravitation can explain the Keplerian orbits, which are ellipses. It can explain also parabolas and hyperbolas. And this is a comet that follows almost a parabola. The ellipse is being so large, you know, it will follow something that's almost like a parabola, and that can be explained with the law of gravitation. That was a great success for his theory. The next big step in studying the comets was done by a close friend of Newton, actually, Halley, who is represented here. Thanks to the equations that Newton came up for the motions of the planets that you could also apply to the comets, then you can calculate all the same, you know, parameters for all the different bodies, the planets as well as those comets. And that's what he did. This is a table he published where he looks at all the different parameters of the different, you know, orbits of comets that were seen through time. It goes back to 1337 up to 1695. And he noticed that one of those objects actually comes back at regular intervals, about 76.5 years, and has the same kind of parameters based on the errors that you have with the observations. But this is a very peculiar object because it rotates in the solar system opposite to the direction of the planets. It's retrograde. So he made the prediction that this was actually a comet that was periodic and that it would come back in 1758. Unfortunately for him, he died like 10 years before, in 1742. But astronomers followed up his work and improved actually on his predictions. And the astronomers of 1758 could find the return of that comet, which is now the comet that we call Halley, based on his name. And if you want your name to appear actually in the sky, if you discover a comet, every comet is named after their discoverer. So, you know, if you want your name up there, you can try to find a comet. All right, so what are those objects? Typically, why we study them is because we want to understand what happened in the beginning of the solar system. Those are the remnants of what happened in the beginning of the formation of the planets around the sun. So you can imagine that initially you had a big cloud of gas and dust that collapsed in order to form a disk, and this is a representation of the disk where the planets formed. And you've got the gas and some small particles of dust that are coagulating together in order to form the little bodies that we'll find now in the solar system, and then they grow bigger and bigger in order to form the planets. Once a planet is formed, it will have a tendency to attract all the dust and all the gas that will form its atmosphere later on, the dust that is located around its orbit. When the sun lights up, all the gas is ejected, and we are left with most of the planets, and small bodies are remnants of that formation. Because you know that the Earth actually evolved from this state. The inside of the Earth actually melted and separated the iron, which is now in the core, with the outer layers. And so you also have plate tectonics. And so if you look at the Earth around you, you cannot see whatever happened 4.5 billion years ago when the planet formed. However, if you look at small objects that were staying there for 4.5 billion years ago and didn't change much, then you can try to study the material that formed the planets. That's what we are trying to do. That's why we're interested in comets and asteroids. The asteroids are mostly rocky material. If they get close to the sun, they don't really exhibit activity. But the comets, because we've seen that before, they tend to have these kind of features, which we call a coma and a tail. Actually, the coma comes from the Latin. It means hair. And that's why the ancients actually called them hairy stars. So that's where comet is coming from. The comets have these kind of hairs, the comas, because they are a mixture of volatiles as well as rocky materials. So here is like a recipe I found online for making a comet atom if you want. We thought we could do it here for you, but it's actually a bit complicated. But what you would need is to take some dry ice, you take some water ice, you mix it with some sandy material, some rocky material, also some organics, like very dark carbon, graphite, things like that. And if you mix all these together, you will obtain something that is solid and that looks a bit like that. It's a bit dark, it's a bit bright, and on the surface you've got gas that is ejected by this material. Similarly to that, you know, when the comet comes close to the sun, the volatiles are actually, you know, sublimated by the heat that it gets from the sun, and it will form the tail of the comet. If you want to watch it on YouTube, you've got the link here. So that's what happens. The comets are actually a mixture of icy material and solid material that formed the planets earlier in the solar system, and they stayed far away from the sun for 4.5 billion years ago. This way, they didn't lose their volatiles. Sometimes, some of these objects actually destabilize along their orbit, and they fall by gravitation down close to the sun. If they reach about 3 astronomical units from the sun, 1 astronomical unit is the distance between the sun and the Earth, it will start to light up and sublimate its gases. And that will create the coma of the comet and its tail. So the tail will be directed opposite to the direction of the sun because of the solar radiation and the solar wind. And we can actually see 2 tails. That's why we know there are rocky materials and volatile materials in the comet, because one tail is directly opposite to the sun because it's very light. It's made of molecules coming from the gases, and so it's pushed by the solar wind, whereas the dusty tail actually will have a tendency to follow some Keplerian orbits, so it will lag behind the tail of the comet. And I think we've got a little experiment to show you how that works. So you can imagine that this is actually a comet nucleus. This is the mixture of rocky and of rocky material and ice. And at the back, you will have the different tails. And so the wind here is obviously the wind from the atmosphere, but in the space you get the solar wind, which will have the tendency to do the same thing. The light volatiles will be pushed by the wind more than the dusty material, which is heavier here. That's good, thank you. And so you see, that's why we got several tails for the comets. Those are the ones that we can see. There are others that we do not really see because of different wavelengths. But that creates a problem for astronomers. Suppose you want, because you have a telescope, you want to point the telescope towards your comet, and you want to study this because this is the material that's there at the beginning of the solar system. Well, if you want to see it, you need the comet to be very far. But it's a small object, so you need extremely big telescope, and we can't really see them properly with that. If you wait for the comet to be close to the sun to be able to see it properly in your telescope, then it's wholly done by its tail, so you can't see it. That's why the best way to actually study the nucleus of the comets is to actually go in situ and send a spacecraft to actually study them where they are in space, far away from the sun. Okay, just to give you, this is a slide to give you a sense of scales for those objects. The nucleus, the mixture of materials from the early solar system, is about 10 kilometers in diameter. The coma around it is about 10,000 kilometers to 100,000 kilometers in diameter, and the tails are millions, hundreds of millions of kilometers long, so they can be the same distance between the Earth and the Sun. So these are objects that are actually the size of a city initially, and they can extend to the size of Jupiter or the size of the, between the Sun and the Earth. These are very, very different scales, so that's why it's very difficult to simulate the whole object as a whole. And just a little note to show that the nucleus, actually, we didn't really know because we couldn't really see the nucleus earlier. It was inferred by Whipple in 1951 from indirect observations, the effect of non-gravitational forces to the nucleus. But until we took a picture with Giotto of a proper nucleus of a comet, we didn't really know that there was a solid material in the middle of the comet. This is a very small note to let you know what happens when the comet impacts planets. We've got an example with Shoemaker-Levy 9 in 1994, which impacted Jupiter. Here you see the different impacts. And if you project this impact, the GG, onto the Earth, this is what it will give. The outer part of the impact is actually here. We think that so those objects are 10 kilometers across. These objects are big enough that they can create global catastrophes on the surface of the Earth. We think that one of them actually helped bring the dinosaur to extinction like 70 million years ago. So that's why we also want to study these objects. That's because they can create problems on Earth eventually if they fall on us. So if we know them better, we'll be able to protect ourselves. All right, I'm going to talk now about the space missions that we've developed in Europe to study those objects. The first one is Giotto. It was decided in the 1980s because people realized that in 1986 there would be the return of Comet Halley. It comes back every 76.5 years approximately. Actually, the next return of the comet will be in 2061. I'm crossing my fingers that I will be able to see it. But those of you in the assembly who are young, you'll probably be able to see it. I wish it for you. It's a relatively bright comet every time, and it's been followed for every return since 240 years before Christ by the Chinese and a variety of people, I mean also India and a variety of people around the earth. The mission was named after Giotto because of this fresco where he depicted the comet Halley also on it. But there's another, many different depictions of comet Halley. But there is a problem if you want to study that comet. I told you earlier, this comet was discovered also because it has very specific properties. It turns around the sun opposite way to the planet. So here, for example, in green, you've got the Earth rotating around the sun, and here is the trajectory of Halley when it comes close to the sun at its perihelion. If you want to encounter that comet, you need to send a probe, and the probe will follow more or less the orbit of the Earth and go close to the comet. That means there is one big major issue you need to take into account. Speed for the solar system. Now we've got many people here. I'm sure several of you know the question, the answer to the question I'm going to ask you. Does anyone know what is the speed you need to have in order to go into orbit using a rocket from the ground? Yes. Yes, 11 kilometers per second. Okay. And another one then, what is the speed of the Earth around the sun? Yes, I agree, it's of the order of 32 kilometers per second around the sun. So when you've got speeds in space, you need to consider speeds that are of the order of kilometers per second. These are very, very high numbers. They are difficult to imagine because typically we've got much lower speeds in our life, right? So those are the speeds I was asking you about. The escape from Earth is 11.2 kilometers per second, right? That's 40,000 kilometers per hour. The International Space Station turns around the Earth at about 7 to 8 kilometers per second. The Earth around the Sun is like 30 kilometers per second. And if you meet an object that goes opposite to your speed, you will add the two speeds, obviously. And the meeting between Giotto and Halley was 68 kilometers per second. That's 245,000 kilometers per hour. Let's compare that with speeds that we know more. This is the speed of the fastest train, the bullet trains. That would be 0.1 kilometers per second. The supersonic MiG-31 plane is like about 1 kilometers per second. The speed of a bullet going out of a nozzle is about 1 kilometers per second. So all those speeds are much faster than bullets. Okay, let's look at what happens if you encounter a bullet in space. So here you've got the effect of a small debris impacting the arm of the ISS. That's about 1 centimeter across the hole through the arm. It didn't prevent the arm from functioning, but you see that if you receive a bullet, it will create a hole. And it will maybe destroy what's inside. Suppose this is a helmet for an astronaut and your head is inside. This is an experiment that was done on Earth. This is actually a carrot instead of a bullet, but it's sent at the same speed as a bullet, 300 kilometers per second. It will clearly destroy the helmet and what's inside. Similarly, if you've got a satellite, even if it's protected by a layer, look at the carrot going and crossing this is cardboard layers, and it destroys completely your egg. And the egg is what you want to protect, whether it's your head or the inside of your satellite. The sensitive, electronics that you have, the computers that you have. Imagine your cell phone or your laptop receiving a bullet. It won't work that well after. So you need to be careful about this. The best way to do that is to use a repel shield from the same scientists who discovered the nucleus. What we are going to do now is to split this cardboard into two different layers. What will happen? Well, you've got the experiment here. The first layer actually is impacted by the bullet or the carrot and destroys and reduces the speed of that bullet. And the second layer actually protects your egg. So separated shields are actually much better because they're also lighter than big, bulky shields. You can think about making a very, very big, thick layer. But if you send that to space, you will need to use bigger rockets. Right? So here this has been used for many missions going to study comets and especially Giotto. You can see the spacecraft here. It's about 2 meters long. And this here is the first layer of the shield to protect the spacecraft from the dust coming from the comet Halley. This is the part that is turned towards Halley. And this is the photo that was taken of the nucleus of Halley. Of course, you cannot take the picture with the camera through the shield because the shield is protecting you. So the camera is actually here. This is the cylinder at the bottom, and it looks outside of the shield. Unfortunately, so it was able to take the first pictures of the comet, especially at 600 kilometers, the closest it went to the nucleus, in 1986. But it received an impact afterwards, and we were not able to actually use it after, because it was destroyed. But the rest of the spacecraft actually were fine. So we've got some fuels here, we've got the antenna to communicate with the Earth, and a number of instruments that were dedicated to study the composition of the gases, to study the composition of the dust, to study, the magnetic fields around the comet, and things like that. And that worked beautifully. These are the results of that mission. Just as a note on the side, Giotto was not the only mission. There were actually 5 other science missions dedicated to Halley. So Vega 1, Vega 2 by USSR, 2 missions by Japan, and 1 mission by the US. But Giotto is my favorite one because it's European, but especially it went the closest to the nucleus. It took all those pictures where you can see the nucleus very clearly of the comet, 15 to 10 kilometers across. It has an active surface. We were talking about sublimating materials, so 10% of the surface of a comet is actually ejecting volatiles. And the composition of the things that the comets are ejecting are very enriched in carbonaceous, hydrogen, oxygen, nitrogen compounds. So those are very interesting elements because if they fall on the Earth, they can help with the emergence of life. We are thinking that some of the early comets that fell onto the Earth, into the ocean, for example, by the kind of materials they could have brought, could have helped with life emerging on Earth. 2 numbers here. The albedo is the fraction of light that the object reflects. These are very, very dark objects. Think about the darkest thing you can see on Earth, like the surface of the roads, or for example, let's take some dehydrated coffee. Those dark materials are not as dark as the comets. They are much darker. And density, 500 kilograms per meter cube. Those look like rocks. And if you mix ice and rocks, you should have a density that's larger than that. Density of water is 1,000. Here you've got half of it. If you put the comet into the ocean, it will float. So that means that this object actually has a lot of void into it. Okay? I'm going to talk about that a bit later again. So a lot of interesting results based on that mission. Next mission we are going to talk about, I was personally involved in that one. This is Rosetta and Philae, the first mission that was able to land on the surface of a comet, 6070 Chandra-Gerasimenko. So let me tell you a bit of story about that mission. But the goal of this one is to actually be able to follow the comet along its trajectory along the sun, to be able to see the onset of activity, and after its passage through perihelion, to detect a number of compositional things, and to study the comet for a long term, to be able to do global mapping, all these things. And this is why you don't have a shield for that mission, because we were going at the same speed as the comet. That was the goal. So the mission was decided after Giotto in the 1990s. It did a rendezvous with 6070 Chandra-Gerasimenko. We already talked about when the comet started to be active. It's about 3 AU. So here we was. The goal was to go to 3 AU and to be able to land on the comet before it got active. That's the size of the spacecraft. The antenna always like 2 meters across to be able to communicate with the Earth. And the largest solar panels that were dedicated to a space mission at the time, it was 64 meters squares because we were going as far as Jupiter. We needed that much to have enough power at that time. 11 instruments were on board. There were more instruments on Philae. I'm not going to describe in detail everything, but typically what you would like to do in order to study those objects is to look at them with different types of cameras at different wavelengths. So here we've got cameras in the visible, in the ultraviolet, in the infrared, in order to detect different things. Typically in the infrared you'll get some signatures for ices and some minerals, and in the visible, in the UV you can get some ions also, and the visible gives you the global shape. Concert, that's an instrument I really like because it was a French instrument that was developed in the laboratory in Grenoble. I was working on it, and it's a radar that allowed us to actually probe the inside of the object. Cosima, Rosina, those are mass spectroscopy instruments. They were able to give us some composition of the molecules that were ejected by the comet, either in the shape of the gases or in the dust. MIRO, GIADA, MIDAS are a set of instruments, so microwave instruments, the dust particle instruments, microscopes. I'm going to show you a few pictures of what the dust look like, and some plasma instruments, and of course, no lander philae, which had another 10 instruments on board, similarly. The mission, I've got a few slides now that I'm going to go through relatively quickly. They give you the different time frames of the main parts of the mission. So the first one was a delay because we were supposed to depart in January 2003, but maybe some of you remember the first launch of Ariane 5, which was our launcher, was actually a failure. So they had to postpone several launches before we could actually use that launcher. And so that's a problem for us because we had developed the whole mission based on a comet, which was called Virtanen, which was actually smaller than 67P Chermov-Gerasimenko, half the size. And so we didn't really know if our instruments would be appropriate for the new comet, but we needed to find a new comet because we changed the date. You know, it's like if you postpone your trip to Mars, you'll lose 2 years of your life. So, similarly, you've got more time to wait for the comet to come back, so we needed to find another comet to go there. So the launch was successful from Kourou in 2004, and then this in red is the orbit of the comet we want to catch. Okay? In blue here you've got the orbit of Earth. The sun is in the center, it's not shown. And here you've got 2 asteroids that we are going to study on the way. But we need several gravity assists in order to have enough speed in order to reach that far in the solar system and to reach the comet here. So first gravity assist is with Earth. Second gravity assist is with Mars. There's 4 of them. And every time we pass by a planet or an asteroid, we'll have the opportunity to test our systems. This is a 10-year journey. So, you know, you want to make sure that everything's working fine. So those images were taken actually by the cameras on board the spacecraft. This is the camera Osiris on board Rosetta, and this is the camera Shiva on board of Philae, which was, you know, piggybacking on Rosetta. So you can see actually in the camera the solar panels of the spacecraft and Mars behind. Another flyby by Earth to do another gravity assist. Here we flew on the night side of Earth, so you can actually see just the lights, but actually this is India here. Oh no, sorry. India is there in the middle, and that's Arabia here. And then we flew by a small asteroid. This one has a very particular shape, which shows that it has been accelerated and is rotating a bit faster than usual. That's why it has a diamond shape. And this is called the York effect. And then another gravity assist by Earth. This is a test of the infrared cameras. Because you probe in the infrared, you can actually look at the continents without being bothered by the clouds on top of the continents. So you can see here, this is South America and North America. You can see the thermal emission from those continents. And then we passed Lutetia, another asteroid from the main belt, image of this asteroid, and an image of Saturn that was behind. Another way to test our cameras. And then by the end of 2010, we put our spacecraft to sleep. That's something that we don't really like to do, because here the spacecraft will be asleep for 3 years, and then we need to wake up in 2014 to be able to land on the comet. So that was a bit scary. All along this trajectory, we waited until we could wake up the spacecraft. The plan was to do an approach of the nucleus, to do a landing, then the passage of the comet at the perihelion, closest to the sun, and then by December 2015, the end of the mission. Successfully, in January 2014, we woke up the mission and it was still alive. So that was extremely good. You see the engineers at ESA were extremely happy, and so were we, the scientists. That was the signal that, you know, that was the ping that the spacecraft actually sent back to us after being awoken. And then immediately we test all the systems, so all the cameras gave us some, you know, images, and we test the engineering system, like the computers and, you know, exchange of information, fuel, all these things. Well, then the next step is to get close to the comet and to land as soon as possible, because when the comet is active, it will eject material that will be more difficult to land, because you won't be able to see properly what's happening, and it may damage also the lander. So the lander Philae, we did some simulations about landing, and we were basing this on observations that were taken by the Hubble Space Telescope. Far away from the sun, we could see the light curve of the nucleus and get an idea of its shape. It was a relatively regular shape, you know, and we based all our models for landing based on that. But there was a surprise for us because the shape that we actually saw was this one. And so that shows you that, you know, when you look at objects that are very small and very far, it's difficult to get their proper properties. And this is a movie that was taken by Rosetta, where you can see we were getting closer and closer, and we were starting to think, where are we going to land on that? This is a very irregular object. It came close to the sun several times. It has a lot of irregular, you know, surfaces that were eroded with time. So we took some time during the summer in order to define what was the best landing site for Philae. Those objects, when you look at them through the cameras of the spacecraft, you think, okay, they're kind of small. You don't really get a sense of scale. So I want to give you a sense of scale. This is the downtown of Pune, right? And this is what the comet looks like if you project to it, approximately. It's not a small object. So this here is about 4 kilometers. It's about 6 kilometers from the head to the tail. And what you can notice already from this object is that it looks like it's two different objects. We'll have to study it better in order to define that. I'll show you later. So we got close to the comet, and even though we were at 3 AU from the sun, it was still already starting to be active. You can see clearly some jets here coming out of the neck of the comet. So you've got the small lobe, the big lobe, and all that. So we really knew that we needed to make decisions fast if we wanted to land safely on the surface of the comet. And look at that. It looks very much like it has been eroded from the neck, and that this material is getting ejected, and that's why you have this very irregular shape. We could take some close-ups of the surface of the comet. So some parts are actually very, very smooth. This is because you've got dust that gets deposited on the surface regularly, and that will have a tendency to, you know, erase the different topography that you can see. But you also have these kind of holes with flat, you know, bottoms and very straight walls. On the surface of the walls, you get some granulosity. Here, the size of those, you know, balls or boulders is about 3 meters across. These may be the first materials that get together in order to form asteroids and comets in the beginning of the solar system. So, decision time. The best place for landing Philae, because we wanted also, there were a number of constraints. We wanted to be able to keep contact between Philae and Rosetta. Philae does not have a big antenna, so we could not contact Philae, you know, from Earth, or get the data from Philae to Earth easily. It needed to go through Rosetta. And we also wanted to have sunlight, because Philae has some solar panels that could make it last longer. The best place was this one that was selected. It's almost smooth, but there's no smooth place on the surface of the comet, so we had to take our chances. And the landing was, so for those of you at the time, you know, it was, there was a bit of media outreach around that landing, because even Google actually gave us a little animation here. The day when we landed or attempted the landing on the comet, the descent was about 7 hours long. And so I'm going to show you a faster video of it. And that was the center of control in CNES, where I was located. The Philae actually was made by the French Space Agency and the German Space Agency together. So we were controlling it. Now I've got a little movie to show you. So you need to decide where to land on the comet beforehand, and you need to launch before that landing site is in front of the spacecraft. The comet turns on itself by about 12.5 hours, and the descent is about 8 hours. So actually the landing site is the opposite side of that small lobe here. And Philae has been ejected from Rosetta. Because it's dangerous to be close to the comet that is active, Rosetta, immediately after launching Philae, is taking another trajectory to be further away from the nucleus. But here you've got images taken by Philae of Rosetta and by Rosetta of Philae, you know, following its trajectory down to the surface of the comet. So this is what it looked like. The landing site is going to be the red dot that appears here on the other side of the small lobe. And I must congratulate very strongly the French Space Agency and our engineers, because the calculations they made for the trajectory was dead on. Like we were less than 50 meters away from that point. The problem is to get attached to the comet. It's a very small body. It does not attract you with gravitation very strongly, not like the Earth. You know, it's like the weight of Philae is about 100 kgs, but if Philae was on the surface of the comet, it would be the same weight as 1 gram on my fingers here. So it's very, very light. So we want to attach ourselves to the surface of the comet. We have 2 harpoons and 1 retro rocket to do that. And we knew that the retro rocket would not work, and the harpoons actually didn't work either. So these are the pictures just before landing, but when we landed, then we got this one. And we knew there was a little problem with Philae because it bounced. The 2 systems that we had to attach ourselves to the comet did not really work. So we bounced back and we crossed that depression that is seen on the small lobe, and we stopped actually behind that little mountainous region in a part of the comet that's not well illuminated. So that was a bit of a problem, that we could not recharge our batteries either. We had enough batteries to last for 5 days, and we did the experiments that we were supposed to do during these 5 days. And for example, we took this picture of the surface of the comet, which interestingly actually looks quite rocky. That's the final panorama that was taken by Philae when it landed. We successfully acquired some sounding through the comet with our radar and did some compositional analysis of the material. Thanks to all the people who were involved with that landing. So landing happened here, but that was not the end of the Rosetta mission. We continued to go along the trajectory of the comet around the sun and study the different types of activities we could see, try to follow out actually the way the topography changed, because you eject materials, so the surface of the comet is changing with time. So we can try to correlate the two, see what the materials what the composition of the materials was being sent out into space at different times. And after that, we prolonged a bit our mission because we had enough fuel, and we landed on the surface of the comet at the end of the mission, like in September 2016. And actually, you've got the same problem for Rosetta as you've got for Philae. You cannot continue to do this forever, because the comet is not attracting you. So we needed fuel all the time in order to change our trajectories and get closer and further away from the comet with time. And when the fuel was over, then that was the end of the mission. We landed on the surface of the comet with Rosetta as well. A few results that I would like to highlight to you, since we are talking about that. The first question that we had was, is this a single object that was eroded, or are there 2 objects here? And people actually studied very carefully the different layers that you can find on the small and the big globes, and those layers don't join. So they demonstrated that those are actually 2 different objects in the beginning of the solar system that formed and probably stuck together early on. Then we could also study the composition of the dust that was ejected from the comet. These are the images that were taken by 2 different microscopes. So Cosima here and Midas on the right side. Those are very, very tiny particles. The size scale here is 0.5 millimeter, around microns. So the little material here that you can see is 10 microns in size. That's extremely small, and you can see this is aggregated dust particles. They get crushed, they are extremely porous, extremely fragile. This is at even a smaller scale, because this is a scale of 1 micron. And the material that is constituting those particles is mostly organics in volume. We've got a little bit of minerals here, but we've got a lot of organic material. That means a lot of carbonaceous compounds, or carbon-rich molecules that are in those materials. We can also study the composition of the gas. I'm not going to ask you to read all this. You can find it online also at the European Space Agency website. But those are all the different molecules that were found in the gas ejected by the comet. The colleagues who worked on that, they like to show it as a kind of zoo of molecules. I'm going to highlight just a few that are of interest for us. Glycine is the king of the zoo because this is an amino acid. I was telling you earlier that the kind of carbonaceous compounds that came from the comets could, help with the emergence of life, and we found amino acids on the comet, so they can help, bring amino acids to the surface of the Earth early on. Then we've got benzene and other long carbon chains. Those are again carbonaceous molecules, methane, all those. So there is a large variety of molecules that are made with carbon in those objects. And then we find H2O, we find CO2. We find also oxygen, which was kind of weird because this O2 was not supposed to be found at this level in that comet because it's very, very volatile. It sublimates at very, very low temperatures, but we found it, and we've got a number of theories to try to explain its presence there, alcohols, and a number of things that are useful. Oh, maybe just one last, the argon, krypton, xenon, those are noble gases. They don't really react strongly chemically, so they can be very good tracers for what happened in the early solar system in the gases. Maybe like this one, that. So as a summary, after Rosetta, this is the picture that we get for the comets. Those are all the comet nuclei that have been imaged by space missions or from the ground using radars. 67P, I was talking about with Rosetta. This is Halley, we talked about with Giotto, and other ones. Now the problem that you will notice here when you look at the name of these different objects is that they all have a P at the beginning of the name. Like this one is 67P, this one is 9P, Halley is 1P. The P here means periodic. Those objects are comets that come very close to the sun regularly. Halley is every 76.5 years. 67P is every 6.5 years. So that means those comets are not really, really fresh. They've come close to the sun several times already before we study them. If you want to study the volatiles that were there at the beginning of the solar system, it's better if the comet has not seen the sun earlier, right? So that's the new idea that we have with the next mission that we're developing for the European Space Agency. This mission is called Comet Interceptor. So the goal of that mission is to actually have a closer look at the fresh comet. So an Oort-Kloot comet, so a comet that stayed very far from the sun for 4.5 billion years and then came closely just now, or even an interstellar object, because we know there are some interstellar objects that look like comets when they get close to the sun. But the problem is that you can't predict those objects, and they are too far to even be able to be seen when they are in the Oort cloud. So how do you do that? Well, the idea that we have is that this mission, which is done by ESA and JAXA, it's a partnership for three spacecraft, will be launched in 2029, and it will be hosted here at the Lagrangian point L2. This is where the James Webb telescope is located. Another telescope looking at exoplanets, for example, Ariel is an exoplanet telescope that we are going to launch with. This is a good place because you can have satellites standing there for quite some time until it's time for them to move. And we are going to have enough fuel to be able to change our trajectory. And if we find a comet suitable that goes not too, that crosses the ecliptic plane, for example, not too far from the Earth, we can fly by the comet. That's the goal. And the probability is, for us, every 2 years you've got a new comet like that should be suitable. And we are expecting to last 3 years there. So let's see what that brings. We've got 3 spacecraft that are going to study the nucleus and the coma of the comet at different distances. 2 European ones, and the JAXA one will be in the middle. We are going to study, of course, the composition of the gas, the composition of the dust, the properties of the nucleus, and the magnetic field, the interaction between the comet and the solar wind, all these things. Beyond that, what's going to happen? Well, if you really want to study in details the kind of material that is forming those objects, the best way to do it is to bring it back to Earth, actually. We don't have enough space in our spacecraft to bring very elaborate or very high resolution mass spectrometers, for example. It's difficult to do that. So if you want to do it properly, it's what you do for asteroids, like the asteroid Bennu and Osiris-Rex mission that came back with the samples last year. You can study them on the lab on Earth, and that gives you a lot more details. We would like to do that with comets. Just a note that actually that's been done for the dust particles of comet, the solid dust ejected by the comet, with Bill-2 and Stardust mission. I didn't talk about it because that was another mission, but it's been done. What we would like to do now would be a volatile return sample. But that's a big problem because you need to keep it very, very cold, At least minus 70 degrees would be good, maybe lower if you can. But then you've got a lot of problems trying to cross the atmosphere of the Earth and bring it back to the surface of the Earth. So those are called cryogenic sample returns. We are working on it. Maybe we'll see that at one point. This is a proposal that was done to NASA about sample return with the volatiles from a comet, and we'll see what happens in the future. For the time being, I will let you dream a bit about the Comet Interceptor mission and the good things that we are going to do about that. And for the young ones here, if you can think about new technologies to help us get the sample return from comets, that would be extremely useful to try to understand those objects, how they can impact us and the beginning of the solar system. And tell me about everyone. Thank you very much for your attention. This will conclude my talk, and I hope you had a good time. Thank you.
Okay, thank you so much, Jeremie. It was basically a very exciting lecture because just how he was explaining how the mission unfolded actually, and he was actually there. So I mean, just to hear the unfolding of the mission, how they landed, it was brilliant to hear. I'm very sure that you will have a lot of questions to ask. So we have Tushar with us, who will pass on the mic. Please raise your hand and keep the hand raised so that he can actually spot you there. Yeah, please, your questions.
Hello, my name is Kamesh. I want to ask that what is the big problem in the problem bringing the sample from the comets? What is the biggest problem in the problem?
Well, that's an excellent question. Actually, I don't think I'm very well placed to tell you which one is the biggest one. But I know there are many problems. So I can give you a list and then we'll see. But yeah, so if you want to bring sample returns from the comets, the way it was done earlier with the Stardust mission is that they actually flew by the comet. The comet is ejecting material. So if you've got something that can collect the material on the way, you'll be able to collect it. So there's two issues with that. The first one is that you will collect the dust particles, but not really the gas. And the second issue is that you are arriving, again, at the speed of a bullet. So most of the materials were kind of partially destroyed or melted when it got collected. So they had a special material to dampen that effect, but we know that some of the particles were affected by that. So that was the issue there. It gave very interesting results on the mineralogy and the composition of the particles. But here, if you want to do a sampling of the comet, especially of volatile materials, well, if the comet that you are targeting is a comet that is easy to reach, it has come close to the sun often. So the material that you need to reach is the material that you need to dig up for. So that's the first problem, is that you need to bring something that will dig several meters down the surface of the comet in order to get the pristine thing. It's not on the surface. You don't have ice on the surface. Very, very little. Then the second problem will be to, you bring everything back to the Earth, but those volatile materials, they will start to sublimate at 3 AU, not at 1 AU. So already when you come back, you will start to have things not in the shape of ice, but in the shape of gases. So you need to be able to trap all those gases. And you need to be able to trap them at cold temperatures. And then, where do you want to study them? Maybe you can start studying in the ISS, because you don't go to Earth. But if you cross the atmosphere of the Earth, it's going to be difficult to keep these things cold. Because you've already seen the missions or the astronauts when they come back with the shuttle or other missions. That gets very warm. So those are all the different problems that we'll face. So, and I think the biggest one is really the temperature.
Good evening, sir. So my doubt is do we have any, what is the percentage of ferromagnetic materials in that comet that we discovered?
Ferromagnetic materials, huh?
Yeah, we didn't see this shown as a list. We don't see any Rn-like substance which should be common.
Yes. So I can go back to that, and then I can show you a slide that I didn't show. It's on the backup. But the minerals here are typically, silicates, pyroxenes, a bit of olivine. Those are the kind of minerals you'll find. I suppose that's what you're asking about. Yes. So it depends on the comets also, the amount of iron you would get into that, but there is a range of different minerals, and you've seen those. I can go back. Why if I can show you the here. So I didn't talk about that mission, but this is the sample return from the comet that happened with Stardust. So that was in 2004. Comet is 81P Will 2. and then it went to C 9P Temple 1. The sample return was from the VLT. And so you can see the shields here that were used, and that part of the mission was constituted of aerogels. So that's very, very light silica material, almost 99% porosity, in order to collect the dust particles in them. And then that's what it looks like. The particle impacts here and gets caught into the silica, and the end of the tracks actually are where the particles are. And in terms of composition, we've got, that one was interesting because, so we get the mineralogy that includes minerals, you know, like pyroxene, olivines, that were melted at 1,500 degrees. So that result actually showed us that forming the comets, you've got minerals that actually were very close to the sun that were mixed with ices that need to stay at the temperatures of Pluto, like 50 AUs from the sun. So that started to give the idea of this large mixing in the protosolar nebula between between these materials that are, you know, the minerals that you're talking about that were formed close to the sun, from, you know, rocks, and the ices that are included in there. Similarly, we found some carbon-rich materials, and there was some peculiar composition that were enriched in sodium, chromium, and potassium. You know, typically, we were not thinking of finding such particles. But if you look into the results of that mission, you'll get a lot more answers about the question you had, especially the fraction of. If you're looking very specifically for the ferromagnetic materials, there will be some numbers that you can find. I don't have them from the top of my head.
Thank you very much for the presentation. I'm Devashish. You said that the interceptor will be kept parked for 2 years at L2. So during that period, I believe it won't have much of science goals directly related to the cometry. So should we keep it on a halo orbit even then, just to remain parked there?
So you want to keep it in
No,
which orbit?
my question is, will that be kept in a halo orbit, or it will remain stable at L2?
Oh no, it will have so those points are.
It's a space flight related issue.
Yes,
more
yes,
of it.
yes.
Yeah.
So those points are a bit stable, but you need to be in a halo orbit if you want to remain stable there. The L1 just like the L2. So that's what happens with ODPR mission.
Yeah.
You know, it's not at a single point in space. You
Right.
need to regularly correct for its trajectory and you put it in a halo orbit around that.
So that also will have a halo orbit over there. So this interceptor also will have a halo orbit there.
Yes.
Yeah.
I think so.
Thank you.
Hello. You mentioned one of the comets has had a retrograde orbit. What could be the reasons for that if the entire ecliptic disk is moving in one direction? Why will the comet specifically be moving?
Well, that's a very, very good question actually. What is making the orbits of the comets? So actually I didn't talk about that, but there are two reservoirs for comets in the solar system. One is called the Kuiper belt, and it's the ensemble of icy objects that are located around and beyond the Pluto orbit. Okay? And those will create some comets. Actually, we know some comets that are prograde and they are following. I mean, 67P is typically a comet that is from the family of Jupiter. It's probably a Kuiper belt object that came in the inner solar system and interacted with the planets on the way. There is another reservoir of icy objects in the solar system which is located much further away, like 10,000 times away. It's called the Oort cloud. And it's called the Oort cloud because when we look at the orbits of those comets, just the fresh comets, then we see them arriving randomly everywhere from the sky. So it's not just a disk shape anymore. It's more like a shell around the inner solar system, if you want. If you look at those orbits, they are randomly located anywhere on the surface of the stars. And anywhere means that if it arrives close to the sun, it can come from any direction and even opposite to the direction that the planets are turning around the sun. But the way you do that is that the comet located in the Oort cloud can be destabilized by a passing star, and the passing star would have, you know, another direction altogether from with respect to the planets. But those would be Oort cloud comets.
Hi, Jeremie. So I'll take this chance to also point out a question which is online, so there are various people watching online. And there's some discussion going on about the water content of the comets. So has Rosetta or others detected how much water has been detected as the composition is one question. And then there's there's a theory that the comets could have brought water to the Earth. So do they have enough water that they could make up all the water which is here, or is it what kind of fraction do you think was brought in by comets?
Yes, that's a very interesting question. And I could have shown some data about that, but let's talk about it. So typically, Giotto measures the fraction of the gases that come out of the comet are mostly due to water ice, water molecules. And so that's 80–90% of the gases you see ejected, they are from water. Then 10% is CO2 and another 10% is about CO. This changes from comet to comet, but those are approximately the ratios. Then you want to know the ratio of the water to the solid mass, to the dust. So the Giotto already made some measurements, and the value that they found was a ratio of 1 in terms of mass. So you got, approximately the same amount of material in terms of mass for the water as well as the dust. But that again changes from comet to comet. And for 6070, there is a relatively higher bar for that, but we think 6070 has much less water. The content in the ratio of rock to water was actually larger, like maybe 4. But similar order of magnitude. Now, in order to study how much water came from the comets to the Earth, one thing you can look at is the isotopic composition of water. So water is made of 1 oxygen and 2 hydrogens. But there is also heavy water that will contain deuterium instead of hydrogen. So the hydrogen has 1 proton and an electron turning around, and the deuterium has a proton and a neutron with an electron turning around. So it's heavier. And if you look at those ratios, the heavy water with respect to the lighter water, on Earth and on the comet, you can guess how much water you can put from the comet into the water of Earth. Because if the comet is enriched in deuterium, you can't put too much because the ocean has a given value. Okay? And what we found with 6070 is that the water of 6070 Chernobyl Arsenicum is very much enriched in deuterium. So most of the ocean of the Earth cannot come from an object like 6070 Chernobyl Arsenicum. Again, those values change from comet to comet, and this is an ongoing study because we are trying to get more and more values for the deuterium. The deuterium will actually tell you how much water you can put. So for the deuterium, that is the content of the water in the comets, and we can compare that to the Earth. But typically, you would expect not more than a glass of water of the ocean of Earth in a liter comes from a comet. So, like maybe at most 1/3. Probably less. And the common knowledge for this, where the water on Earth comes from, is it probably came from a lot of the icy asteroids that we have in the main belt. Because the water for those asteroids typically has a deuterium value that is fitting also well with the Earth, unlike the comets.
That's interesting and exciting information.
Good evening, sir. I just had a question about the Comet Interceptor. You mentioned that it's going to hover around the Lagrange 2 point for approximately 2 years. So is the trajectory of the comet that you are targeting predicted, or is it going to hover there until the comet that you require is within the reach?
So your question is related to, do we know the trajectory of the comet in advance? And unfortunately, no. Because we want to discover a new comet, something that has not seen the inner solar system beforehand, we are going to ask all the astronomers to find suitable targets before the end of our mission, when we don't have enough fuel to actually go and catch the comet. So we don't know it in advance. The statistics tell us that every 2 years we should have an appropriate comet, maybe more, but approximately. And we are going to last probably 3 years, maybe a bit more. We take margins, so the space missions last longer than they should, or than they are warranted for. And so, you know, we have good hopes to find a comet that is fresh and that will have the right orbit. So an orbit that will be close to the Earth at one point where we can reach from our space missions. But we don't know. And we are crossing our fingers that it's going to work. We can't know it in advance.
So is the Interceptor equipped with extra fuel if it has to survive for another 2 or 3 more years?
No, it will fly with the fuel that we can put on board. So it's, you know, but, you know, hopefully everything will work out. But we can't guarantee it in advance. Worst comes to worst, so interstellar objects, that's really need to be lucky. We've got a few, but outcross comets, there are some that should come within reach. So that should be, and we've got survey telescopes on the ground that take surveys of small bodies further and further away that should help discover new comets that would have the properties. So as soon as we see one that would have the right properties, we'll need to make a tough decision actually. Suppose you launch and you are in L2 and you've been in L2 for 2 months. And you discover a comet that could work. But is that the good comet? Do you want to wait more for another one that may have the right properties, you know? Now you need to make a decision. You've got enough fuel for 2 more years. Do you want to wait more? Now we are going to have a lot of discussions to make sure that the comet that we choose to go to will be the right one. If no comet comes, then we will not lose the mission. We are probably going to retarget it to another comet. There are many comets. There are 200 periodic comets that we know of. So some will be available if we want to go to another comet that has already seen the sun. That would be, you know, downgrading the mission, but we'll still study comets with that.
Just want to point out that the IUCAA is part of the Vera Rubin telescopes, I think LSST, and the many survey telescopes which are coming up, which will be used by astronomers to do like large-scale surveys and find these transitory orbits, objects very fast. Maybe before that happens,
Yes,
it could be a factory of transient finders. Just pass on to you.
As you taught earlier that there is a presence of water on comets. So I want to ask that how that water came on that comet. So
So I will go back to the picture I had earlier, I guess. Beginning of the show. So if you think about what's happening in the beginning of the solar system, you've got volatiles, gas fractions, that are condensing in order to form the sun and the planets around it. Here, those things. Okay? And you know that most of the fraction of the gas that you have here is hydrogen, and then you've got helium. But then you've got other, you know, gases, including water, and water is relatively common because hydrogen is common and oxygen is common. Okay? So those objects are cold, and the gas that is surrounding them, if it's water, it will condense onto the surface of the particles. Okay? So you've got, when you form the planets, and if it's far away from the sun, you know, you will have a tendency to have the dust particles located in the disk around the sun and where you form the planets. And those dust particles that are cold will collect the ices that will, you know, then stick onto them and form those particles. So H2O is common because hydrogen and oxygen are common. CO2 is also common because carbon and oxygen are also relatively common.
Please raise your hands if you have questions to ask.
One more doubt, sir. Sir, like you told that jet that comes out consists most of water or H2O. So, like how it should be the solid form when it was formed. Comet, the water should be the solid form, and when it comes out, it comes in the spray form. So, why it's a sublimation, not going to the liquid then to the gas? Why it's sublimating from the solid to the gas directly?
I'm not sure I understood completely the end of your question. You're wondering about the sublimation of water?
Sir, like you have said that when the jet comes from the comet, it comes in the form, consists most of H2O, right?
Yes.
And when the comet would have formed, it would be solid ice.
Yes.
So like when it comes under the solar radiation, how it goes directly from solid ice to the gaseous vapor? Like it should have been in for some time doing for the liquid state also, no sir?
Oh no, there's no pressure on the surface of the comet, so it will go directly from the solid to the gas phase and it sublimates. So that's the thing. It doesn't go through liquid water.
Sir, but the ice formation should be subsurface, not on the surface, na?
Yes?
The ice should be under the surface of the comet, na? Not on the surface.
Yes, this is why I told you if you want to get to the volatile, you will need to dig under the surface of the comet to reach it. The surface of the comet is depleted in ices. Yes. So this image actually is just to show you the kind of material that we are thinking about. But once you have sublimated the ices that are on the surface will be dry. And that's what actually we see on the surface of 67P. Most of the surface, you don't actually have water ice on the surface of the comet. Most of it is black and kind of dry. If you want to have the pristine volatiles, you need to dig several meters, at least 1 meter below the surface in order to get it.
Okay.
Okay.
Sir, there are actually like many comets that we have been observing over the centuries. Usually like the probabilities of them colliding with Earth are like almost negligible. But I want to ask that like is there any specific comet that we used to observe periodically before, but later on it collided with some other celestial object like in its trajectory? So like is there any specific comet that I could read about more?
Okay, is there any, maybe I didn't understand completely the end of the question, but earlier you said, is there any comet that we studied and then impacted an object, right? Yes. So the typical example would be that one. That one. Shoemaker-Levy 9 is a comet that we studied before it impacted Jupiter. It was a comet, it was detected in the sky by Shoemaker and Levy, and then it went very close to Jupiter, and the gravitational pull of Jupiter actually pushed, extended the comet, and the comet split into those different pieces. Okay, and then it was in orbit around Jupiter for several months before each of those pieces of the comet impacted Jupiter here. So that's a comet that we could study earlier in advance before it impacted Jupiter. We were very lucky to actually see that. To my knowledge, there's no other comet that we studied that impacted a planet like that. But the problem with the comets is that, except for the 200 periodic ones, most of the fresh ones we can't really predict their orbits, so we don't know what they will impact. And it's also even more difficult because you see, those objects, they eject matter. What is making rockets move into space? It's when you eject gas as well. So you've got the same, the same physics here. The gas that is ejected by the comet will push it, and it will change its orbit. Every time the comet goes close to the sun, its orbit changes a bit, or sometimes a lot. So those objects have a tendency to change their orbit by themselves. That's what we call non-gravitational forces, and that makes them very difficult to predict over time. We study a lot more the asteroids, and you've got a good idea of what asteroids may impact the Earth with a long-term scenario. So, like for example, there's Apophis, which will pass close to the Earth in 2029, if I'm not mistaken, and that would be interesting to study. But yeah, the comets are difficult to predict for the impact.
So there are only three space missions for comets which have been taking place in the European Space Agency, or there are more? Because I believe is it a combination or a collaboration with European Space Agency and NASA, or is it just the European Space Agency? And there are quite a number of space agencies, right? Other than both of them, like JAXA, and then there is CNSA, and then there is quite a number of them. These the three ones that you mentioned, were the three missions for comets, right?
Yeah.
Were there any more missions other than the three by European Space Agency?
So the European Space Agency has made many more other missions for space, but not for comets. These are the three ones for studying comets in particular. But for example, for studying Mars, we've got Mars Express and
just for comets. Just for comets.
But just for comets, these are the three. And they are, I call them ESA space missions because, ESA is a major, builder of the mission or contributor to the mission. Comet Interceptor is actually a collaboration between ESA and JAXA. ESA will provide 2 spacecraft and JAXA 1. For Rosetta, we had a collaboration with NASA because NASA provided some of our instruments. But most of the operations and everything that was, so all the operations, the landing, everything was done by the European engineers. And similarly, with NASA missions to Comets, we've got sometimes instruments coming from Europe as well. So there's always collaborations in different missions, in that way. But those were the ones where European Space Agency was like major contributor.
I have just one more question. I hear, because I read a number of newspapers, I wanted to know, there are quite a number of news where it's been said that an asteroid will hit the Earth and the Earth will be destroyed, and it's been happening for many years by now. So how much truth is in it, and is only asteroid that can hit the Earth, or there are other objects which can hit the Earth and destroy the, yeah.
So the impact with the Earth is asteroids or comets. Those small objects, we don't expect the other planets to be able to move and come and impact the Earth. But asteroids and comets are the potential dangers for us. The problem with comets is that we can't really predict very well their orbits, even the ones that we know very well. So we study mostly the asteroids, and there's a lot more asteroids that get close to the Earth because they're near-Earth asteroids typically. And most of them will not impact the Earth for at least 100 years or something. Some get very close to the Earth, but most of them we know will not impact the Earth anytime soon. But of course, there are unknowns here. For example, we study mostly when you look at the sky, at night, and you want to see the objects around the Earth in the sky. When you look during the night, that's what the astronomers do. But that means that you're always looking towards the external part of the solar system, towards Mars, Jupiter, all those planets. You don't really look between the Earth and the Sun, and we don't really know if there are asteroids that could impact the Earth that are located there, between the Earth and Venus or Mercury. So that's one unknown, and we'd like to have some telescopes looking at that. Actually, when we send missions to Venus, some of the telescopes are used to look around. So there is this unknown that there may be asteroids that we don't know well that are located between the Earth and the Sun, and they could impact us. And then there is another problem, is that the size of the object. I told you, if you've got a very small object and it's far away, it's very difficult to detect with telescopes. And so I don't really have a slide on that, but typically the global catastrophe for the impacts are located at 1 kilometer and more size objects. And for those, we know 99.9% of all the asteroids that are this size or larger. Okay, so those are well known. If you've got a smaller asteroid, like 100 meters across, that can destroy a city on Earth. But those, we don't know all of them. I think we know maybe half of them. Because they're more difficult to detect, they're smaller. So they've got less light. And so that's where the next surveys for asteroids to prevent asteroids impacting the Earth will focus, because we want to prevent asteroids that can destroy significant infrastructures on the Earth, like a big city. And so those are the sizes, 100 meters, 150 meters across. Those are the kind of asteroids that can present a danger right now to the Earth for the impact. And if they are too small, like 10 meters or 1 meter, those get destroyed when they cross the atmosphere, they will burn out. So they don't present that big of a danger. So the big danger for asteroids right now is the asteroids that we don't know well and that can present a danger in the 100, 200 meters size range. Okay? And that can happen, just to tell you something about statistics.
Sorry.
And because we don't know them, that can happen any time. It could fall on us right now. We don't know.
So as taxpayers, we should tell our governments to build more telescopes or spacecrafts detecting comets rather than nuclear bombs or something like that, right? Please, I mean, this is the truth. Please support more astronomers. Let's take one last question. Tushar, there's one hand at the back. Thank you.
Is there any significance behind tail of a comet in this mission? Hello?
Yes.
Is there any significance behind the tail of a comet in this mission?
So you are wondering about the tail of the comet, but I'm not quite sure.
Is there any significance, like during this mission is the any importance given to the tail of a comet?
Oh, okay. So one thing that can happen with the tail of the comet, so the space mission, usually they try to get as close as possible to the nucleus. So they'll study this object and the gas around it. But you're right, there are some interesting things that can happen with the tails of the comets. We study a bit the interaction between the solar wind and the tail of the comet with some of our instruments. So we've got magnetometers and detectors for the solar wind and the energetic particles in order to detect things. Like for example, we could definitely show that Chernobyl Gerasimenko does not have a magnetic field, and when it has created its coma, actually it creates a bubble that protects it inside from the outer part of the solar wind, from the energetic particles. There's some stuff like that. But the space missions is mostly dedicated to studying the small scale of the comet, not really the tails. There are space missions that will study the solar wind and the interaction with the tails of comets, but at a further distance. So usually it's done by telescopes, either from the ground or telescopes on spacecraft. But those spacecrafts are not dedicated to the nucleus of the comet.
Okay, so thank you so much for such a wonderful questions and also very detailed answers by Jeremie. Before we leave, we'll like to tell you that we'll be coming up with our next public lecture very soon. Please keep in touch with our social media channels and you will get all the information there. If you have any questions, you can always, on Insta and everything, you can just ping us and just talk with us. Okay. So before we end this, let us thank Jeremie again for this wonderful talk. Thank you so much.
Thank you very much.
Thank you. Okay, so if you wish to listen to this lecture again, we have already